Good morning, friends. Let us start chapter 2, classification, structure and solidification of materials. Everything around us, including ourselves, is made from combination of hard, hundreds of stable elements. Metals. So there is example of substitutional alloy. Intrametallic compound is composite of sets. Substitutional alloy. The example of brass, reddish atom of copper, and the gray atom represents zinc. Intermetallic compound. Composed of set of atoms bonded each other. In this example, each gray atom is bonded to other gray atom and 4 orange atoms in the same plane. The direction of bonding will be the same for each set of atoms. For sake of simplicity, out of plane bonding is not presented. That is intermetallic compound. Interstitial metal have alloying elements that sit between the regularly arranged atoms. They tend to be slightly too large to be properly fit and will cause distortion of the nearby atom. Basic properties of metal. Metals tend to good conductors of electricity and heat. They are often malleable. That is, they can extensively deform without fracturing at room temperature and relatively high strain rates. They are relatively hard and strong at room temperature. Metals cannot be made transparent unless the metal is thinner than the wavelength of visible light. For example, with physical vapor deposition, aluminum can be formed in thin enough layers to see through. Also, anything thin than visible light is transparent. They can be made stronger or tougher by the thermal and chemical treatment as well as mechanical strengthening methods. Some metals such as ferrous, cobalt, nickel have desired magnetic properties. Metal can be remelted and recycled. Malleability. Atoms in metals are arranged in very orderly manner, but some of the electrons are not strongly bonded to any particular atom. It is a cloud of electrons. Malleable means easy to, known as dislocation motion means easy to roll, easy to work, harden, cold work. That is malleability. Conductivity and other factors. Conductivity to conduct electricity. Abundance of metal. Properties of ceramics. Ceramics keep their strength at high temperature, higher than most metals and polymers, and their resistance to most chemicals because the strength and stability of their bonds. The properties most ceramics can be summarized as ceramics are electrical and thermal insulators. Ceramics are strong. Ceramics are very sensitive to notches. Small cracks can initiate fracture and result in catastrophic failure of the whole structure due to low toughness. Ceramics are chemically stable. Some ceramics are used as soft or hard magnetic material. Sorry, one. Ceramics are chemically stable. Some ceramics are used as softer hard in magnetic material. So large quantity of ceramics are used in building materials, including concrete blocks, bricks, cement, plasters, ceramic tiles, and refractory tiles. Resistance to high temperature. Semiconductors conduct electricity better than insulators, such as most ceramics and polymers, but not well as most metals. Most semiconductors could be classified as ceramics, but some of the polymers, ceramic semiconductors, can be modified with chemical impurities, which drastically change their electronic properties. Adding the impurities is called doping, which is similar to alloying, except the alloys are usually included in amount of order 0.01 to 10% by weight. Doping is usually in the order of part of billions to part of per thousand. Intrinsic semiconductors, materials that have two energy states close enough for electrons to jump over the full state of empty conduction band, are called intrinsic semiconductors. So there are silicon, germanium, all these intrinsic semiconductors, gallium, arsenide, indium, antimonide, cadmium sulfide, zinc telluride, all these. Intrinsic semiconductor. They are pure semiconductors. With doping is different. Precise measurement to elevated temperature are made using thermistors, which is made from intrinsic semiconductor. So pure semiconductor are these. Road signs, safety streets runners, shows rely on the phenomenon called fluorescence and all. Extrinsic semiconductor, in this case, impurities are added in small, carefully controlled amount of number of atoms to provide either electrons near the conduction band N-type or energy level near the valence band P-type semiconductor. Silicon. If an element with 3 electrons in the conduction band is added to this above things, silicon, for example, aluminum, boron, gallium, indium, a p-type semiconductor, clever combination of n-type, p-type extrinsic semiconductors are used for junction devices, diodes. Diodes allow high current flow only in one direction. Rectifiers are arrays of these diodes that change alternating current into direct current. Another type of light emitting diode, LED, used in digital displays, where electrons in the conduction band move to the valence band and that process light emitted. Another critical semiconductor device is transistor consisting of 3 semiconductors arranged in a PNP or NPN combination. Transistors serve either as a gate or amplifier. Millions or even billions of transistors are incorporated in cheap or integrated circuits. The polymers name comes from Greek word poly, that means many, and mers, that means parts. Much less stiff, that is for the same load. They deflect and deform much more than metal, ceramics, at a time. For example, 30 times more than steel. Some plastics. At room temperature, many plastics creep or slowly deform with time, which can cause undesirable deformation and lead to breaking. Thermosets are less strong than metals. However, they often have low density, so their strength divided by density might be close to that of metal. Expandable when heated, a rate at which 10 times higher than the metal. They also soften and melt much lower temperature than most of the engineering material. Flammable to different degree, chemically inert, do not corrode, but most of them disintegrate with repeatedly exposed to UV radiation. Some polymers, for example nylon, absorb water and swell. Most plastics are more affordable than other engineering materials. Most thermoplastic polymers are extremely ductile and malleable and can be easily formed into complex shapes. The same is true for thermosetting polymers before they are cured. That is probably the main reason they are so often used for everyday life and are gaining a competitive edge in engineering application. Bioplastics are biodegradable. Other thermoplastics such as fluorocarbons, resins have advantageous wear properties. The bonds between adjacent long chain molecules in their monoplastic are about 10 times weaker than the bonds between atoms within the long chains. These weak bonds, called secondary bonds, determine the overall strength of the polymer. Therefore, thermoplastic polymers are generally less strong and melt at lower temperature than thermosetting polymers. Semi-crystalline or amorphous. Thermosetting polymers. The thermosetting polymers, long chain molecules, are cross-linked in three-dimensional arrangement so that often whole product become a used molecule. Cross-linking, also called curing, can be done at high as well as room temperature with the help of chemicals. Thermosetting polymers, also called thermosets, exposed to additional heat will burn and char just like a cake left too long in the oven. Composites are combination of two or more materials where each material can be visually distinguishable from each other. Wood, marble, and granite are natural composites. Properties of composites are greatly influenced by the type of matrix and the type of shape, size of reinforcement material used. Composites are stronger than unreinforced matrices. High performance polymers with thermosetting matrix can have a specific strength, that is strength per unit weight, higher than metals. Composites with a thermoplastic matrix are not so strong, but they are stronger than unreinforced plastics. Composites are corrosion resistance. Composites used in everyday application are often less expensive than materials they replace. The example, concrete is more often used, cheaper and tougher than tiles or stone for paving roads. For example, steel planes are made from composite with special coating or skins made of radar absorbent material, RAMs. Biomaterials. Biomaterials can be implanted in the human body without causing adverse biological reaction or rejection. Nearly inert, porous in growth, surface reactive, absorbable. Nearly inert means ceramic device replacement of cemented and pre-fed into the bone. Porous in growth, without using cement or press fitting due to the porous nature of the ceramic, bone ingrowth occurs, attacking the ceramic implant to the bone. Attach direct. Surface reactive. Ceramics attach themselves directly by chemical reaction to the bone. Absorbable. Ceramics are absorbed into the slowly replaced by the bone. Ceramics are used to hip and knees replacement as well as the dental bone growth and implants. One widely used application involves ceramic tooth caps, and artificial tooth teeth made from the porcelain. Polymers are often used for heap replacement. Nanotechnology, nanotubes and fluorescent structure. One of the allotropic graphene is the form of carbon monotubes. Each nanotube represents one molecule. The diameter of tube is on the order of 100 nanometer, which in length is much greater. Each nanotube consists of millions of carbon atoms, and both ends are capped with hemisphere resembling one half of a soccer ball, so-called Eulerian structure. These tubes are extremely strong and stiff, relatively ductile. They have comparatively low density and are electrical conductors. On the basis of these properties, carbon nanotubes are called an ultimate fiber because the carbon compound bond is so strong. They are extremely promising as a reinforcement of composite material. Nanorobot automated manufacturing are being developed so the novel system can be manufactured as well as current precision manufacturing operation accomplished at a significantly lower cost. Shape memory alloys, nickel, titanium, copper based alloys, copper zinc alloy, and copper aluminum nickel, as well as some iron alloys are materials that change their crystallographic structure with temperature, and once the temperature is restored, revert the previous crystallographic structure. So simply stated, they can determine the room temperature but change back to their original shape when heated. So they are called shape memory alloys. Shape memory alloys are also used for eyeglass frames, collapsible antennas, greenhouse window openers, clamps, connectors, easy to install fasteners, fitters, self-extending coronary stents. Piezoelectric ceramics, often called piezoelectric crystal, material that produce a voltage when they experience a change of dimension, strain, under an applied load. This effect is reversible. Magnetostrictive material, the behavior with which analogous to that of piezoelectric ceramics, except they respond to magnetic field. That is, they produce a magnetic field when strain is applied or produce change in dimension, strain when a magnetic field is applied. Like piezoelectric ceramics, magnetostrictive materials are also used for ultrasonic transducers. One suggested application is for paints that can change color to indicate corrosion and the metal underneath them. Foamed aluminum, blowing air into the molten metal and trapping the fourth that forms in the surface. When the fourth solidifies, it becomes foam. Chemical vapor deposition on a polymer or carbon latex that later burn away. Sleep casting powder into the polymer foam. Doping molten or powder metals with titanium hydride, which are the casting of sintering temperature of the product. Release of hydrogen, leaving a large number of cavities in the structure. Carbon foam with very finely dispersed porosity called molecular foams have isotropic properties that equal in 3 directions and can be shaped directly into complicated aerospace structures. This shows an example of metallic foam. One interesting development is so-called aerogel, discovered in 1930 but getting more attention recently. It is not a gel but foam, considering gas and the solid silicon, not liquid and solid. As a strict definition of gel requires, the aerogel is stiff, is silica-based substance, 97% air. It is lightest of all solid materials known. You cannot feel the weight when held in your hand. However, when dropped on the hard surface, it bounces and rings like a piece of light metal. Frozen smoke or pet cloud, although it is nearly as light as spider web, Aerosol is surprisingly strong. Metallic glasses. Metallic glasses are composed predominantly of iron, nickel, and chromium, alloyed with carbon, phosphorus, boron, aluminum, zirconium, and silicon. They are formed with special technique such as a splat cooling or melt spinning, in which molten alloys are propelled under high gas pressure at a very high speed against a rotating copper disc chilled surface. They can also produce by vapor deposition and electrochemical deposition. Each atom consists of nucleus composed of proton positively charged particle, arbitrary convention, and neutrons which are not electrically charged. The nucleus is relatively stationary and very small, about 10 to the power minus 14 meter. It is encircled by a thin atom, thinly dispersed moving electron cloud of every varying density so that the diameter of the atom is in the order of 10 to the power minus 10 meter. So 10,000 larger than the nuclei or nucleus. Both proton and electrons have an equal magnitude of electrical charges, 1.6 into 10 to the power minus 19 coulombs. But the charge of electrons is considered negative, while that of protons is positive. Scanning electron microscope or transmission electron microscope, atomic force microscope, scanning tunneling microscope. You can see the atom through it. The atomic number referred to as Z number, the number of protons in the nucleus. Z number is the proton in the nucleus. For a neutral atom, the completely without missing the electrons, the number of protons equal to number of electrons. So they are only here helium, neon, argon, krypton, xenon, and random. Noble gas, stable substance, or more, you can say molecule. I'll not go for mass and all. Atomic bonding. Electrons exist around the nucleus in orbits with different radii, with representing a different energy level. Only two electrons, which must have different spins, can have same energy level. Some different energy levels are combined into cells. The electrons that occupy the outermost shell are called valence electrons, and these electrons are extremely important. Some atoms have stable electron configuration: helium, neon, argon, krypton, and xenon. They are inert. So they are like this. Helium is 2, then 2 plus 8, 2 plus 8 plus 8, then 2 plus 8 plus 8 plus 18. So that's how the orbits are known. The nomenclature of outer orbits or MNO PQ like that. They are in orbits. Near is 2, then 8, then 8, then 18, then 18, like that. In general, chemical bonding between atoms can be divided into two groups: primary strong bond, secondary weak bond. Three different types of primary bond are found in solids: ionic, covalent, and metallic. Ionic bonding: metals have more protons than electrons each atom, therefore they are positively charged. Cations, non-metallic materials accept one more extra electron, negatively charged anions. Ionic bonding, perhaps the easiest to describe and visualize. It is always found in compounds that come both metallic and non-metallic elements. That is NaCl. If you say simple salt, that is eating salt or table salt, sodium with chlorine, sharing of electron, the table salt. Sodium atom loses one electron while the chlorine atom gains one. So there is ionic bond. Like first is 2, then 8, and 8. If it is not less, it is less than 8, then it is unstable. Covalent bonding. Covalent bonding, stable electrical configuration achieved by sharing the electrons between adjacent atoms. So two atoms that are covalently bonded will each contribute at least one electron. So it is for hydrogen. Metallic bonding, as name implies, found in metals and alloys. Metallic materials have one or two or mostly 3 valence electrons which are not bound to the particular atom in solid. So which means that there is room in each atom for electrons to travel in valence band. They are free to drift throughout the entire material and are considered to belong to the metal as a whole. Metallic bonding, zinc schematic secondary bonds. Will not go too much to it. Secondary, also called van der Waals bonds, are much weaker than the primary bond. Crystallization, essentially the metals, except when cooled at extremely rapid rate. A major fraction of ceramic materials and certain polymers crystallize when they are solidified. So these are the common unit cell structure, body-centered cubic. So there is 8 atoms at the corner and center 1 atom. So 9. FCC, face-centered cubic, 8 at the corner on the face 6. So 14 atoms. Then hexagonal close packed. So you have hexagon 6, 6, 6, 12 plus 2 plus 3. So 12 plus 5, 17. Schematic of body-centered cubic. Schematic of face-centered cubic. And schematic of hexagonal close packed. Amorphous means without order. Crystalline, which can form a regular repeating 3-dimensional structure called crystal lattice. Amorphous can aggregate with no particular order. Thin film of lubricant, metallic glasses, polymer, and gels. Residual stress. When FCC iron is cooled to room temperature, surface of the part is cooled fast and transformed into BCC structure, body-centered cubic structure. The surface expands while the interior is still hot and has the FCC structure. When the interior cools down, and transform into BCC structure, it will start to expand, but the exterior, already cold and strong, tends to prevent this expansion. As a consequence of this tug of war situation, the surface is stretched and the core is compressed so that the forces in part are in equilibrium. The volume of material increases or decreases slightly depending on the type of applied force, tension or compression. Stress-strain ratio. Anisotropic stress-strain ratio is modulus of elasticity. Anisotropic behavior, if the whole piece of material is only a crystal or the crystals are oriented in the same direction, the material would exhibit anisotropic behavior, meaning its properties vary with direction. On the other hand, if the crystals are small, usually are and randomly oriented, the material is isotropic, means that identical properties in all directions. Plastic deformation, permanent or plastic deformation. You cannot change it. You cannot return it. That's it. Equilibrium condition, the condition, the material when all reactions are completed and the structure should not change regardless of how long the material is kept at that temperature. Phase, a material having the same composition, structure and properties everywhere. There is a definite interface between the phase and any surrounding or adjoining phases. Solid solution, solid single phase that contains more than one element. Solid mixture, solid material that is where more than one phase is present. Alloys, substituting one type of atom with another in a structure referred to as a substitution solid solution. Squeezing one foreign atom between the atoms, material referred to as an interstitial solid solution. You already seen producing a mixture of two or more different phases. Solubility. So copper atoms and nickel atoms can substitute each other in any quantity. So they are soluble in, they have unlimited solubility because they are same size. This is because copper and nickel atoms are even closer to each other, and in size the electron structure are about same, and both of them have FCC crystallographic structures. That's why solubility is more. Steel at higher temperature, 912 degrees centigrade, 1674 Fahrenheit, is an interstitial solid solution with carbon. So steel is interstitial solid solution. The strength and hardness of alloys are greater than those of pure metal. Almost always, ductility of alloy is much lower than that of pure metal. Only rarely as copper zinc alloys does the solid solution increase both strength and ductility. So in case of these two only. Electrical conductivity of alloy is lower. The loss of strength used a high temperature due to creep is improved. So high temperature tensile strength will improve or creep strength will improve. Mixture, when the solubility limit of material is exceeded by adding too much another material, the second phase forms. As we've seen, where we add too much zinc or copper to the too much sugar to coffee. Polymer is material soft and tough. A strong and hard glass or graphite fibers are added for reinforcement. Tungsten, titanium, and other carbides matrices of cobalt as a binder. All uses for cutting edges of cutting tools. Decrease the conductivity of copper caused by various impurities. Copper nickel phase diagram. Liquidous line, solidus line. So in between there is phases, two phases, liquid plus solid. An equilibrium phase diagram graphically illustrates the relationship between the temperature, composition, and phase present in the particular alloy system. It is collection of curves showing solubility limits for different composition at different temperatures. Single and multiple phase region. Pure iron melted temperature this 1538 degrees centigrade. Iron carbon diagram. This is called iron carbon diagram. This temperature he is telling about this year 1400, 1350, something like that. He's telling, but here it is showing about delta state is 1450 degrees centigrade. Below that is solid state, austenite state, delta, sorry, gamma stage. So gamma stage is austenite stage. Below that, within the different carbon content are there, iron carbon phases, 0%, 8%, 0.8%, 2%, 4%, 6%, like that. And here is ferrite alpha iron inside. After this, ferrite and cementite, lead perlite, all these things are there. You can see yourself. Sorry. Pure iron melts at temperature 1538 degrees centigrade. Left side of the diagram, figure this. So PCC crystallographic structure, delta iron phase. At 1394, the structure changed to FCC structure, that is gamma iron phase. The ability of solid material to exist in multiple forms of crystallographic structure is known as polymers fission. So it exists in other metal or ceramics such as titanium and zirconium. Pure iron contains up to 0.008% carbon. Steels contain up to 2.11, and cast iron up to 6.67% carbon. To make concept little easier, remember we will use analogy with cloth material colors. Red cloth, pure primary color, only one phase equivalent to single phase. Purple cloth, indistinguishable mix of blue and red as substitutional alloys such as brass, interstitial alloys such as austenitic and stainless steel. With purple, we cannot distinguish between red and blue colors. Red or purple cloth with blue dots, a mixture of 6 spheroid, and red cloth with blue stripes, different microstructures such as perlite, a common microstructure in steel. So this is AC3, this is AC3. AC3 is upper critical temperature. Lower critical temperature is this one, 723 degrees, 750 degrees centigrade. Upper critical temperature is this side is 950, around 850 to 950 degrees centigrade. The lowest temperature at which austenite can exist is 725, say 727 degrees centigrade. That is eutectic steel. Here, perlite, eutectoid, only perlite. So here 727. So below 912, BCC structure pure iron, called alpha iron or ferrite. Ferrite can contain maximum 0.022 carbon. On the boundary side of equilibrium steel phase diagram, we find cementite carbide as iron carbide. Cementite is very hard and brittle. Perlite is ductile. Ferrite is ductile. Ferrite is soft. Iron cementite mixture with more than 2.1% carbon is called cast iron, not iron. Perlite is important to mention a special microstructure called perlite, which is present in most steel and cast iron at room temperature. It cools slowly under equilibrium condition. This microstructure has alternating lamellas of cementite and ferrite. Steel with approximately 0.77% carbon, entirely perlite microstructure. Different heat treatment quenching martensitic formation in steel. When steel is quenched, cooled rapidly from austenizing temperature to entirely different type of a transformation occurs. The austenite transfers to martensite. Martensite is metastable and has the same composition that of austenite from which it forms. But instead of face-centered caving, the structure it has a structure known as body-centered tetragonal BCT and very hard, brittle. Depending on the chemical composition of steel, the hardness can be as high as 65 HRC. So after this hardness, you have to temper it. Need tempering after normal this quenching, normalizing and annealing process. Intermetal annealing is used to remove strain hardening due to previous cold working and restore ductility so that additional cold working can be performed. That is process annealing. Full annealing is normally used for steel's medium carbon content 0.35 to 0.65 carbon to improve machinability and permeability. Steel is first fully austenized at the temperature reached at 25 degrees centigrade above the so-called SC3 line. Then there is a solid solution of total, there is a total phase of gamma region. Then it is cooled slowly in furnace. Normalizing the process used to homogeneity alloy steel austenization as per approximately 50 degrees centigrade. Here 25 to 30, 50 to 60 degree above the SC3 temperature, and for a short time. This is for a long time, short time, and then air cooled. This is slowly in furnace, this is air cooled. Stress relieving to relieve the stress, EWST. These stresses are particularly present in steels due to expansion of iron, transformation from FCC to a BCC structure upon cooling. So small changes will be there. Residual stresses will be removed. Hidden hazards in design of manufacturing and should be minimized. The most common method of residual stress mitigation is by heating to temperature substantially below the austenitic ferrite transformation to allow some diffusion of atoms in short distance. The heating is then followed by slow cooling. Edge hardening. So aluminum were quenched from elevated temperature from are supersaturated with solid atoms at room temperature. This alloys then etched at room or slightly elevated temperature. This strengthened by process known as edge hardening, precipitation hardening. Several alloy systems, including copper, beryllium, follow this mechanism. Strain rate is defined as rate of change of the strain with respect to time. The strain rate is a variable that can change from very low rate observed creep to extremely high strain rates during impact or shock loading. High localized deformation known as adiabatic shear. Adiabatic shear, the bulk of plastic deformation of the material is concentrated in narrow bands within a relatively underformed matrix. Influence of temperature, thermal effect. Phase change, basically melting and boiling. Dimension change, elastoplastic changes, brittle, ductile, chemical change, other physical changes such as drying, segregation, outgassing, thermal effects due to non-thermal causes, for example, frictional heating, electrical heating, and this. Excessive humidity, corrosion, condensation, storage issue, problem associated with environmental control. Corrosion is an undesirable process, can be defined as degradation of material due to the reaction with its environment. Degradation implies deterioration of physical properties of the material. Electrolytic reaction, Fe plus 2E minus, then 2H plus 2E is H2. So this is the main cause behind corrosion of steel. There is localized corrosion, pitting, revised corrosion, filiform corrosion, galvanic corrosion. So what is localized corrosion? Attacks target area that material pitting crevices are filiform or localized type of corrosion. Pitting results when a small or cavity forms in the metal, usually as a result of depassivation of a small area. Crevice corrosion is another type of localized corrosion that occurs in confined space where the access of working fluid from the environment is limited. Crevice corrosion occurs under gasket and seals. Filiform corrosion occurs under painted or plate surface when the water breaches the coating. Galvanic corrosion occurs only when two electrochemically dissimilar metals are contact. So, like zinc and steel, so one is become anode and one is become cathode. Cathode corrodes slowly, and anode. So cathode is less corrosion, and anode is sacrificing anode. That is zinc. Corrodes faster. Environmentally induced corrosion. Material that is the result of presence of a corrosive or chemically reactive environment, like salt water, brine water. That is brine water. Stress corrosion caulking, hydrogen embrittlement, liquid metal embrittlement, corrosion fatigue, alternate environmentally induced corrosion depending on environment and types of loading. Flow assisted corrosion. Flow acceleration corrosion results when the protective layer of oxide on a metal surface is dissolved and removed by wind or water. Then another corrosion, then next. The erosion assisted corrosion. Impingement or cavitation are the example of this type of corrosion. Erosion corrosion is an accelerated increased rate of this deterioration or attack on a metal because of relative movement between the corrosive fluid and the metal surface. Intragranular corrosion occurs the result of localized attack or near to the grain boundaries of the metal or alloy. De-alloying or selective leaching refers to selective dissolution of active metal phase from an alloy in a corrosive environment. Brass containing copper and zinc are one of such examples. Material being anodic to copper dezincification in a corrosive medium. Fritting corrosion occurs as a result of replaced wearing, weight, and the vibration. Rough surface corrosion resulting in pits and grooves occurs on the surface. Fritting corrosion is often found in rotation and impact machinery, bolted assemblies and bearings, as well as surface exposed to vibration during the transportation. Transportation or use, no problem. Fritting corrosion is most important. Corrosion protection, coating the metal, alloying the metal, removal of oxygen, corrosion inhibitors. So any of this will help to coating the metal with zinc, organic coating, resin, alloying the metal with chromium, nickel chromium, removal of oxygen, and corrosion inhibitors. So if you put anodic inhibitor, cathodic inhibitor, then corrosion will be less. That is control, not stop. For instance, pure copper can have a perfect crystallographic structure. However, by adding zinc to copper, it obtains brass. Despite of imperfect crystallographic structure, brass has more superior properties over pure copper. It is harder, stronger, less expensive to produce. Actually, the goal of alloying element is to produce imperfect structure but with improved properties. If the crystal have missing or have few extra atoms, the imperfection is called a point defect. In particular, one of few atoms are missing, the term as a vacancy. Vacancies can result for imperfect atomic packing within the lattice during the crystallization process. Dislocation is the line of imperfection representing a missing row or an extra row of the atom. In otherwise, perfect crystal. If one extra line of atoms is squeezed in the part of crystal is shown in figure. This is called line dislocation or edge dislocation. So there are some dislocations. Edge dislocation. So one direction, the opposite direction. Screw dislocation is this. Dislocation movement in the crystal, screw dislocation, edge dislocation. So in screw dislocation, both are moving apart. And in edge location, the direction of this dislocation motion, it is slightly rotating, and this is just opposite. Slip, that is the slip plane. The process which dislocation moves and causes material to deform is called slip. However, as a spring, if a high level of stress is applied, the material will experience permanent deformation. Strain hardening occurs during the plastic deformation at room temperature, that is, the material is cooled worked. Strain hardening means it will take small more load before fracture. The material is deformed in the higher temperature. Atoms will have enough energy to move and relieve internal strains. So as soon as dislocation are formed, they are dissolved and the material will not strain harden. So it will remain soft to form. Otherwise it will crack. It will go for a total dislocation. It will crack. Grain boundaries. Earlier we mentioned dislocation pile up in the grain boundaries. The individual crystals in the metal, other crystallographic ceramics and polymers are called grains. You can rocket grain boundaries using metallurgical microscope. To smoothly polish mirror-like surface and obtain chemical etch short period of time, then process is called etching. You can see these grain boundaries. Influence of grain boundaries. What happened with the grain atoms with atoms at grain boundaries are more reactive. They form chemical bonds. The grain boundaries stop dislocation. So small grains, large amount of grain boundary, we have stronger at room temperature. If they are large grains, the small grain boundaries, so not stronger. At elevated temperature, the effect of reverse material with small needs to be less energy to melt. So that is slightly different. Hot shortness is caused by local melting of a constituent or an impurity populating the grain boundaries. And then what will happen? The material is subjected to hot work. The metal can crumble and fall apart along the grain boundaries. That is antimony in copper and brass. That is the problem. Recrystallization. Recrystallization lowers the strength of material but makes them more ductile. Diffusion is just statewise migration of atoms from one position lattice to another. Self-diffusion, activation energy. Self-diffusion, copper nickel alloys. The movement of atoms is random and atoms in are identical. This type of diffusion called self-diffusion. General rules regarding diffusivity are higher temperature provide higher diffusivity because large number of atoms have the activation energy required to break atomic bonds and become free to move to new location. It is easier for small atoms to move into lattice of large atoms. Diffusivity is higher in materials with weaker atomic bonds. Atoms have higher diffusivity and less dense crystallographic structure. Diffusivity is higher in the materials with small grains because they have more grain boundaries with more spacing. Diffusion can be undesirable when two parts stick together. Diffusion is the main mechanism in many thermal treatment process, annealing, tempering, and others. Surface treatment process, carburizing, nitriding, and doping. The powder technology process where the objects are formed from particles through diffusion. Hot work and cold work. Cold work products are harder and stronger than the hot work product. So when you go above AC3 temperature, and then you work or you do some work that is hot work. Below that it is cold work. Below AC3 temperature, if you are rolling, forging, doing anything, that is cold work. You are going above any mechanical thing that is above AC3, that is hot work. Rolling, forging, all these things. Extruding, recrystallization and grain growth. Recrystallization can be defined as the nucleation of growth of stress-free grains. Recrystallization that occurs during deformation is called dynamic recrystallization. Static recrystallization when it occurs after deformation. Recrystallization may occur in a discontinuous manner when a new grains form and grow in a continuous manner when the microstructure gradually evolves into a recrystallized microstructure. Recrystallization occurs when the uppermost temperature limit of the recovery range is reached. With the onset of recrystallization, minute new equiaxed grains start appearing in the microstructure. These are formed by a group of atoms known as the nucleus. Mostly nucleation start at the site of dislocation pileup, slip planes, grain boundaries. Plastic deformation is the main reason for recrystallization, and the plastic deformation leads to dislocation pileup at the slip planes and the grain boundaries, which become point of high internal energy. When recrystallization temperature is reached, these high energy regions, highly deformed parts, give away part of energy as heat of recrystallization and form nuclei of small strain-free grains, which initiate the recrystallization process. Process of grain growth. Grain growth is also inherently associated with recrystallization. Part of the heat is recrystallization is absorbed by surrounding atoms so that they have sufficient energy to overcome the rigidity of the disturbed lattice and become attracted to the lattice structure of the strain-free grains, initiating grain growth. A larger grain will always be the lower free energy and smaller grains due to associated reduction in the grain boundary area. This is driving force towards grain growth, since any structure will always try to attain the lowest energy state. Although the rigidity of the lattice opposed to this, at a higher temperature, the rigidity of the lattice is lowered and thus grain growth is accelerated. Thank you, gentlemen.